Hi everybody, this is Miss Makano, and today I wanted to do a little bit of review for the periodic table, which is our unit 4. Alright, so the periodic table, as you know by now, was put together by Dimitri Mendeleev, and he ordered the elements that he had at the time into rows. He started off by ordering them by increasing mass. But he also realized, which was his genius of producing this table, was that he realized that elements were not only to be organized by mass, but also by similar properties. And so he came up with this arrangement of the periodic table in which we have groups and we have periods, and there's a very definite pattern. It's what we call periodic law as to how the elements are organized, and we're going to see a little bit more about that. What also gave Mendeleev's periodic table a lot of credibility and validity later was that he actually was able to predict, based on his arrangement of the existing elements at the time, even though he was missing quite a few elements, he was able to predict that one day those elements would be found. And so this is a view of his periodic table that he had at the time. He did not have all the elements, but he was able to predict very accurately what elements would be found and some of their properties even. So that was amazing. So periodic law, as we discussed in class, is basically the idea that as we go across the periodic table, as we go across these periods, which are the rows of the periodic table, things repeat in a predictable pattern. Okay, so the properties of these elements that are in the periodic table will repeat from period to period. So here's period 1, period 2, period 3, and as we go across these periods, the properties will end up repeating over and over, and we will see a little bit more about that coming up. Two important pieces of information that you definitely need to know about the periodic table are that the elements are arranged vertically into groups. So these columns that we see on the periodic table are actually called groups. And the horizontal rows that we see on the periodic table are called periods, and they look something like this. This is just one group taken out of the periodic table to show as an example, and this is one period. So let's talk a little bit more about groups. So the groups of the periodic table, you have some examples shown here with these arrows. What's really unique about them is that elements in the same group have the same number of valence electrons. And just this statement right here has a lot of ramifications that are very, very important and we need to know about. Okay, but that's one thing that you need to understand and remember, that every group, elements in that group have the same number of valence electrons. So for example, group number 1 shown here, all of those elements would have 1 valence electron. In group 2, all of those elements would have 2 valence electrons. Group 3 would have 3 valence electrons, 4 is 4 valence electrons, and so on until group 8, which would have 8 valence electrons. So for example, this is just kind of a cutout from the periodic table. This is group 2, so this would be this group right here. All right. That's just zooming in on it. So these are the elements in group 2, beryllium, magnesium, calcium, and so on. Also showing it right here in the whole periodic table. And if you were to draw Bohr models for these elements, for example, beryllium, right here, we have a Bohr model. And you all know how to draw Bohr models now from our previous unit. What you will see is that beryllium, when you draw its Bohr model, it ends up with 2 valence electrons. Valence electrons meaning those electrons that are in its outermost energy level. So right here. If you were to draw a Bohr diagram of magnesium, magnesium's right here on the periodic table. Same group as beryllium. Well, you would see that you end up with, for magnesium, you end up with 3 energy levels, but the number of valence electrons, meaning those electrons in its outermost energy level, is also 2. And all of these elements in the second group, in group 2, would end up having 2 valence electrons just like this. And if you want to prove that to yourself, go ahead and draw Bohr models for them, and you will see that you will always end up with 2 valence electrons for all of these elements. Let's talk a little bit more about these valence electrons because they're really important. They really determine a lot about the properties and the reactivity of all these elements. So valence electrons are located, as we said, in the outermost energy level or the highest energy level of an atom. So for example, here we have a bunch of atoms from different groups, different periods. But what I want you to focus on is this outer energy level that is drawn in red. Okay? So in that energy level, that's where the valence electrons are. And why are valence electrons so important? Well, because they determine the reactivity and the chemical properties of elements, which is really important. They determine which elements are going to react with which other elements and so on about different chemical properties about them. As far as valence electrons, atoms want to have 8 valence electrons in order to be stable. So basically, all atoms want to complete what we call their octet. Octet is just a word that means 8 valence electrons. So all atoms want to complete their 8 valence electrons in their highest energy level. That's what they want to have. Why do they want that? Because that's what makes them the most stable. And I have a little bit of an analogy here as far as what stable means, stability. So we discussed a little bit about this in class, but if you look at this analogy with this ball going up and down this dip, right? So you can see if I were to place my ball at A or at B or at C, would the ball want to stay there? No, it would not. It would want to roll down, meaning that that ball is not stable where I put it. It doesn't want to stay there. If I put it at E, F, and G, would it want to stay there? No, it wouldn't. It would also want to roll down. So that is not stable. But if I place my ball at D, it would stay there. Okay, so that would be a stable position for that ball. So just kind of using this analogy, we can think about stability of atoms. So atoms, if they have 8 valence electrons, if they have their octet, they are stable, they're happy. If they don't have their 8 valence electrons, they're going to want to somehow achieve that octet. They're going to want to somehow achieve those 8 valence electrons, and we'll see how that is. So for example, if you take sodium is, let's go right here. So sodium is in the first group on the periodic table right here. It is a very reactive group. And what makes it reactive is that, as we said, the first group has 1 valence electron. It's group number 1. So sodium, if you were to draw its Bohr model, you would see that you would end up with 3 energy levels like this. But in the last energy level, you would only have 1 valence electron, which is this energy level right here. Well, sodium is not happy with just 1. It wants to have its octet. So the easiest way for it to achieve its octet, to achieve its 8 electrons, would be to basically get rid of this 1 electron, give it away. And then if it gives it away as shown here, well, then you can see that its next energy level is full. It has 8 electrons, and now sodium is happy. How about chlorine? Well, chlorine is basically on the other side of the periodic table. It's right here in group 7, also a very reactive group, the halogens. So if you were to draw a Bohr model for chlorine, you would see right here in orange that you would end up with 1, 2, 3, 4, 5, 6, 7 electrons on its outermost energy level, 7 valence electrons, What that means is that that chlorine really wants to get another electron to complete its octet. Really, really wants that electron. So chlorine and sodium are actually a very good combination because sodium wants to give away its electron. Chlorine wants to get an electron. So they're going to get together, they're going to bond, and this is what table salt is. NaCl is just salt. And they are very reactive together. Sodium and chlorine are very, very reactive together. And this is what makes them reactive, is this needing to have their octet completed. Okay. Now let's move a little bit into periods. Periods are the actual rows on the periodic table. We don't really call them rows, so we call them periods. And the significance of the periods is that each period tells us how many energy levels we have if we were to draw a Bohr model of those atoms. So for example, period 1 right here in pink, if you were to draw a Bohr model of those elements, you would end up with 1 energy level. In period 2, you would have 2 energy levels, period 3, 3 energy levels, and so on, okay? So for example, for these atoms, potassium, krypton, they are in the 4th period. So let's go, and so right here, 1, 2, 3, 4, right here, this is the 4th period on our periodic table. So we would expect all of these elements to have 4 energy levels. And that's what we're seeing here, 4 energy levels, 1, 2, 3, 4. 4 energy levels, meaning 4 rings when we draw the Bohr model. All right, the other thing you need to know about the periodic table is how to identify metals, metalloids, and nonmetals. And I really like this chart over here because it's very clear. Basically, it shows in blue are all the metals, and you guys did an activity on this in class, so this should be review. Metalloids are in orange, and nonmetals are in green. So you can see that the metalloids almost make what is called like a staircase a little bit. It has a little bit of that shape. And if you look, everything to the left of the staircase is metals. Everything to the right of the staircase is nonmetals. A little bit more about these guys. So metals, so everything in blue here, they are good conductors of heat and electricity. Why? Because they easily give away their valence electrons. They don't hold on to their valence electrons as much as these guys over here do. So because they can shift their valence electrons, that makes them good conductors of electricity and heat. Let's skip a little bit to nonmetals. Nonmetals, which are right here in green, they are not good conductors of heat or electricity. And that is because they really hold on to their electrons. Like we saw about that example we did with chlorine. These guys over here in group 7 all have 7 valence electrons. They just need to get 1 more to complete their octet. There's no way they're going to want to give away any of their electrons. And because they don't want to give them away, that makes them poor conductors. Metalloids, which are these elements right here in orange, they tend to be a little bit in between metals and nonmetals. So they are called semiconductors. And they tend to be better conductors at higher temperatures than at lower temperatures. So they have a little bit of mixed properties of metals and nonmetals. And finally, let's get into some of these groups of the periodic table. And actually what I'm going to do is stop right here, and I'm going to make a completely new video just reviewing some of these groups of the periodic table that you guys should be familiar with for your test and in general. All right, I'll see you in the next video.